Check it out now, y'all.
nanoHUB-U, online instruction.
Hi, we're back again. This is lecture 5 of week 2. And in this particular lecture, we're going to try to summarize some of the important results for contact mechanics. And these results will be very useful in trying to describe how a tip comes into contact with a substrate. So, you know, it's useful to have some broad overview of what contact mechanics is. And it's really an attempt to predict the stresses and the deformations that occur when one solid object comes into another. And of course, there's a variety of constraints. Many of them are geometrical that have to be taken into account in order to get an accurate representation of actually what happens. So, purpose of this lecture is really to review classic results that are well established and published in the literature, because we'll be using these results when we try to interpret atomic force microscopy data. So let's start with a simple question. What happens when you push a tip into a solid slab of material with a certain force F? Well, there are many different approximations that you might make to that physical situation. Perhaps the first attempt to describe this occurred in 1885 when a point force was applied to a substrate, and the deformation D that occurs is a function of radial distance from the application of that force, is written down in this equation. The deformation depends on the Poisson's ratio and the elastic modulus, the Young's modulus of the substrate, and it depends on the magnitude of the force applied, clearly. The problem with this model is that it predicts a singularity at r equal to 0, and that's really not physical, but of course it's not possible to actually have a point force. So this is a nice entry into the discussion, but it's not very realistic. Perhaps another model that could be considered is what happens when you have a circular cylinder that's pushed into a substrate with a force F. Well, if the diameter of that cylinder is 2r, and if the the Young's modulus of the cylinder is E2, the Young's modulus of the slab is E1, there's also Poisson ratio for the slab in the cylinder, nu1 and nu2. Then from mechanics, you can calculate that the deformation depends, as shown in the equation underneath this slab. The deformation is linearly proportional to the force. The proportionality constant is this quantity E star that's defined. Yet another model would be to model the tip in terms of a cone-shaped object. The half angle of the cone is theta, right? And again, you have to define an effective elastic modulus or effective Young's modulus of this system. That's defined by this parameter E star. And in this particular case, you'll see that the maximum deformation, or the force produces a deformation that's quadratic, with a proportionality constant that depends on geometry and this parameter E star. So this is yet again another geometry that you might consider to model how the tip interacts with the substrate. But it's useful to have an overview of what contact mechanics actually predicts, and basically contact mechanics within the context of AFM predicts two quantities, right? One quantity is the contact radius, and in this particular slide, that contact radius is denoted by the parameter A. And then the second thing we're very interested in predicting is the indentation. And in this lecture, the indentation is going to be represented by the parameter capital D, right? So we want to develop some simple models to predict these two quantities when you take a smooth sphere and push it into a flat substrate with a force F. The basic problem involves solving a general set of equations with boundary conditions that are appropriate to the geometry that's specified. So, in particular, we're interested in the contact radius of our sphere when it's pushed into the substrate with a force F. We're interested in predicting any adhesive forces that develop between the sphere and the substrate. Now, these adhesive forces are going to be related to the chemical interactions between atoms in the tip and atoms in the substrate. We're interested in the contact radius of the sphere, for instance, at zero load. So just when the sphere touches the substrate, it'd be useful to be able to predict that quantity. We'd also like to be able to predict the pull-off force. In other words, after we make contact, after we load the tip into the substrate, how much force is required to actually lift off or pull off the tip again. And then lastly, is there a contact radius and separation that we can predict? So to answer these very fundamental questions, right, there have been three classic models, three classic theories that have been developed over time. The first one was by Hertz. The second one was by Johnson, Kendall, and Roberts. That's referred to as the JKR model. And then the third one that we'll discuss in some detail is the Darriaga and Mueller-Toporov, the DMT model. What we need to do is we need to develop in some detail a tip-sample interaction model. We've already discussed one such tip-sample interaction model. That's the one by Darriaga. This goes back a few lectures. And you'll recall that in that discussion, we related the adhesion force. In other words, the force required to separate a tip from a substrate. We related that to the interaction potential energy that occurs when the tip and the substrate are separated one from another by a typical atomic constant A0. The proportionality constant between the adhesion force and the interaction potential energy at equilibrium separation, that proportionality constant was just the radius of the tip times 2 pi. So that's an example of a contact mechanics model that could be developed to try to describe this process of the tip coming into contact with the sample. But that's a very simple approximation, a very simple model. More realistic models are going to relate the adhesive neck that forms when the tip is pulled away from a substrate, and so that's going to relate to the pull-off force in a very important way. So we'd like to try to incorporate that into our discussion of the tip-sample interaction. So the classic tip-sample interaction models are sketched out schematically in this diagram. Perhaps the first model was the one developed by Hertz. Hertz just considered two spheres, radius R1 and R2, that came into contact one with another. This model was developed in the late 1880s. The appreciation of surface forces between atoms and molecules in sphere 1, atoms and molecules in sphere 2, that appreciation was not incorporated in the model. So the Hertz model has none of these surface interaction forces. In 1971, the JKR model was introduced. The JKR model is useful if one of the samples is reasonably soft, if one of the spheres is reasonably soft. And in particular, the JKR model just includes forces between atoms and molecules in the region where the two spheres are in contact, one with respect to another. An advance was made by Bradley in 1932 when he took into account the interaction potentials between atoms and molecules in sphere 1 and atoms and molecules in sphere 2. And that model was fully developed in the DMT model. That's around 1975, where now you actually have long-range interactions possible between atoms in the tip and the substrate. And in particular, the DMT model focuses on the sphere plane interaction. So it's a model that tends to be used very often in discussion of atomic force microscopy. Now, a key aspect in all this is that these surface forces that act between atoms in the tip and the molecule, these surface forces are a result of these surface energies that we discussed back in lecture 2 of week 2, right? If you'll recall, these surface energies were described by this parameter gamma, and we discussed the work required to separate two surfaces one from another, right? So if the materials are identical in principle, the work required to separate these two materials is just twice the surface energy per unit area, 2 times gamma 1. We're going to use that notation extensively here. Just want to point out that there are a variety of different textbooks with a variety of different notations. We're particularly interested in this interfacial surface energy called gamma 1,2. Gamma 1,2 shows up as the energy required, or is the energy that results when surfaces 1 and 2 are in intimate contact one with respect to another. If the two surfaces are separated, right, then two new surfaces are formed. Those two, the surface energies, or the energies required to form those two new surfaces are referred to as gamma 1 and gamma 2 if the material or if the experiment is done in a vacuum environment. If the experiment happens to be done with a surrounding medium 3, then very often you'll find that these works to create the energies required to create the surface, or these surface energies gamma, they often are denoted by 2 subscripts in order to make clear what's being referred to. So I just try to make that clear with the notation that's shown in the slide here, and we'll try to follow this notation throughout the rest of this lecture. I'd like to just collect the important results from the Hertz, the DMT, and the JKR model in this slide. We're not going to derive these quantities. The standard results are often just quoted in the literature and used. The derivations can be quite long and involved. But the point of this table is to summarize the results, right? And in particular, we're summarizing 3 things. We're summarizing the pull-off force, the contact radius that results, and the deformation D that results for each of the 3 models. So common notation in this slide, F is referred to as the force that's applied to a sphere when it comes into contact with a substrate. For the Hertz model, the pull-off force is 0 because there's no interaction between atoms or molecules in the tip and in the substrate in the Hertz model. However, when you move to DMT or JKR model, right, there are adhesive forces that result, and so the pull-off force that you would, in principle, be required to apply to remove the spherical tip from the substrate is related to these quantities W132 that were defined in the previous slide. The proportionality constant between the energies and the forces is geometrical. It always involves the radius of the tip. Now, the presence of these adhesive forces changes the contact radius from the value predicted by Hertz, right? So in the case of the DMT model, the adhesive force that results when the tip comes into contact with the substrate, that adhesive force has to be added to the applied force in order to get the necessary radius of contact that forms when the tip comes into contact with the substrate. In the JKR model, the same thing applies. The relationship, though, is just a little bit more complicated. It involves square roots of forces, as I've indicated. And then lastly, the deformations that result are listed in the third column in this table, right? The Hertz and DMT predictions for deformation are pretty straightforward. The JKR model for the deformation that results is a little bit more involved. It requires an explicit inclusion of the adhesion force predicted within the JKR theory, right? The consequences of this JKR adhesion model is indicated in this slide, at least qualitatively. The adhesion arises fundamentally from these short-range interactions between atoms and molecules in the tip and the substrate. That's the assumption of the model. The implication is that when the tip is removed from the substrate within the JKR approximation, it's possible to deform the sample, as I've shown schematically here, right? And there's going to be a minimum radius that describes that contact before separation occurs, right? So that's again a parameter that the JKR model predicts. It's a fair question to ask, what's the limitation of all three of these models, right? And this is something that I constantly try to remind students that work with me. These results that I've just described are classical in nature, and that means they basically are not including any sort of surface roughness due to atomic corrugation. In fact, they're not even taking into account surface roughness due to pitting or corrugation that resolves because of, let's say, etching or whatever. When the surfaces are rough, these models will start to fail. They won't be applicable. I guess it's probably more correct to say you have to take into account the surface roughness. So you have to develop a model that adequately takes into account the surface roughness before you can start to apply these equations and get results that you can believe. So that's something you always have to remember when you read the literature and you find different research groups apply these models. They're assuming this surface roughness is basically zero. It's probably worthwhile to work through a quick example just to show you how the units work out, how the quantities work out. In this particular example, we've got a Hertz contact with the tip radius 30 nanometers. We apply a 1 nanonewton force to this tip and we push it against the substrate. Just to make matters simple, we pretend that the tip and the substrate have elastic modulus on the order of 200 gigapascals. We're also assuming that the Poisson ratio for the tip and the substrate is 0.3. So you always have to calculate this effective elastic modulus. That's calculated in the first set of equations here. You find out that the effective elastic modulus for this particular example is about 146.5 gigapascals. You can take the formulas in the equation in the table that I gave in the previous slide. You can evaluate that for, let's say, the contact radius. So you can find that in this particular case, the contact radius is only about 0.6 nanometers, not very big at all. It's atomic resolution. I'm sorry, it's atomic dimensions. And of course, this prediction will always limit the lateral resolution in atomic force microscopy, right? So if that contact radius starts to become large, then you start to wonder what the lateral resolution of your atomic force microscope is going to be. In this case, it's pretty small. It's a little bit bigger than an atomic dimension. The deformation that occurs, in other words, how much does the sphere indent the solid? That's on the order of 12 picometers. Again, that's just calculated by a straightforward application of the formulas that you find in the table. If you want to pull this sphere away from the substrate, the Hertz model would predict that you need zero pull-off force. And the zero pull-off force is simply a result of the fact that there's no adhesion between the tip and the substrate. So I also like to calculate the contact pressure that results. The contact pressure is just the force applied divided by the area over which that force is applied. And in this particular case, you'll find that the contact pressure is approaching a gigapascal. That's on the order of 9,000 atmospheres of pressure. It's clearly a very large number. Do I believe that result? Probably not, because I don't know what it means when you apply that force over a radius that's only 0.6 nanometers in size. So these numbers have to be taken, I think, with some eye towards skepticism. You just can't believe these things. But nonetheless, these are the results. This is an example of the predictions that these models allow you to make. It's a fair question to ask which contact model to choose, and there's been extensive work in the literature that guides you in this regard. What I like to do is I like to say that the contact model that you choose is related to the ratio of the diameter of the contact region divided by the typical separation between atoms in the contact region. So you can invent a parameter, which is basically the width of that elastically deformed neck divided by the atomic spacing. And if you read the literature, you'll find that there are two parameters introduced. One is called mu and the other is called lambda. Neither of those parameters have any dimensions, but basically they're trying to measure the width, the ratio of the width of the contact region to the atomic spacing. And you can use that parameter, in this case we're using the parameter lambda, whatever value that achieves, right? You can make a plot of lambda versus a normalized force. The normalized force is basically the ratio of the applied force to the adhesion that results in your sample. It depends clearly on this parameter W1 sub 132. It also depends on the radius of the tip that you're using, right? That's on the y-axis. On the x-axis is this parameter lambda, which is basically a measure of the ratio of adhesion to elasticity. And depending on what parameters you use for the tip and the substrate, you'll land somewhere on this plot. And depending on where you land, right, you can then make a decision about which model of contact mechanics is appropriate to your situation. I just wanted to point out that there's a region shaded in light orange. That region shaded in light orange is due to the Maugis-Dugdale model for contact mechanics. It's a rather complicated model that bridges the gap between DMT and JKR in a rather complicated way. I just show you some of the results that you would find in Maugis' original article, where he actually connects DMT and Hertz, or Hertz and, it allows an interpolation between Hertz, DMT, and JKR. And it all depends on the appropriate value of lambda that you choose, right? So the plot on the left here, bottom left, shows how the penetration varies as a function of loading force. In this case, you're approaching the sample from the left, and depending on your particular value of lambda, you would then have to select out one of the curves on the chart to actually map out how the penetration is going to go as a function of the loading force. Similar plot is given for the contact radius versus penetration. Again, the assumption is you're coming in from the left. You make contact at the origin, and then depending on what your parameters are and which model you choose, you have different penetrations for the force. Different penetrations as a function of the contact radius. So This is just more for information than anything else. It just shows you how complicated this gets, and it gets complicated very quickly. So I think we're going to sum up by just saying that the next lecture will actually move us into combining these contact mechanics with intermolecular interactions. It'll start to move us into calculating or simulating the interaction forces that result when you push on a sample with a tip of specified radius. And so if when we discuss this material, we'll get a much better sense of how these different contact mechanic models can be incorporated to describe atomic force microscope experiments in some detail. So come on back and we'll discuss that in the next lecture. Thank you.